Okay, good morning everybody, and welcome to this session about space transportation. So I'm Thomas Panozzo, and I will walk you through this presentation, which is roughly about 2 hours, and it will drive you through the different steps, and it's about space transportation. So as we are going to see in the summary, first of all, I'm going to give you a brief description of the European launch vehicles. So the different way that Europe has to get to space. Then I want to walk you through the mission analysis process. So we're going from theory up to the reality. So we see how you really do the things. And then at the end of the presentation, we're going to get through some pictures and video from actual real launch campaign in French Guyana, where all the European launchers are launched to space. So I'll try to be as clear as possible, and let's go. So first thing, as a starter, the 3 launchers. So you know that ESA, the European Space Agency, has developed 3 launchers to access the orbit, and they actually they work in a very efficient way because they are operated from the same spaceport, which is in Kourou, in French Guyana, and they provide a complete range of lift capabilities. So the 3 launchers is Ariane 5, Soyuz, and Vega. And as you can see from the graph standing on the lower part of the slide, so the Vega is the launcher for the small payload, and it can launch from 50 kilograms to, I would say that the reference mission is 1,500 kilograms to low Earth orbit, so 700 kilometer circular orbit, okay? When the Vega has reached its maximum performance capabilities, which is 1,500, then the Soyuz take over, and the Soyuz is what we call the medium mass launcher for very specific mission like LEO Earth orbit or GTO or escape orbit, because with respect to Ariane 5, it has the specificity of having a reignitable upper stage. And the Soyuz, you can launch from roughly 1.5 tons, 2 tons, up to 4.5. So that's the range of Soyuz. And then when the Soyuz has reached its maximum capability, Ariane 5, which is really the heavy lift horse work for GTO, with the specificity of being able to launch 2 satellites at the same time, one over the other. But we are going to specify this point a little bit later. And with Ariane 5, you can go up to 9-10 tons to GTO orbit, but to LEO orbit, you can go up to 20,000 kilograms, so 20 tons, which is the case for the ATV, you know, the automatic transfer vehicle that is launched from French Guyana up to the 450 kilometers International Space Station orbit, and then dock to the space station. And that vehicle is as big as a double-decker bus, you know, the red one that you see in London, and it's 20 tons at takeoff. So it's a really, really big toy. So as you can see, these slides, in the last 30 years, the European Space Agency has been able to develop a range of launchers which satisfy all the needs from 50 kilograms to 20 tons. Vega, Soyuz, and Ariane 5. Let's start and describe a little bit the launcher, you know, and see what about the data that characterize the launcher. So the Ariane 5 ECA is a 3-stage launcher. So the first stage is EIP, solid rocket booster, EPC, cryogenic core, and ESCA, which is the upper cryogenic stage. So the first stage is solid, and the EPC and SCA are cryogenic. So cryogenic means liquid hydrogen and liquid oxygen, and very low temperature mixed together. They give incredible ISP, and they are using lots of launcher, and this is the case also for Ariane 5. Just very quickly, the EAP, so there are the 2 big stage on the side. They are filled up with 250 tons of solid propellant, and they give a vacuum thrust of about 500 tons. Okay, so you have 2 of them, And the main one is the consumption, just to give you an idea. So at takeoff, the solid rocket booster, they consume 2,000 kilograms of propellant per second, just to give you an idea. So it's huge amount of propellant that is consumed. And basically they work for 2 minutes, as we will say later, because after 2 minutes, they run out of propellant, and as soon as they run out, they are separated from the launcher. But they are really the one that give you so much thrust at the beginning to be able to lift the whole launcher. Then you have the EPC on the central column, which is the cryogenic stage. Very complex stage because it has only one engine, the Vulcan Joule, very performing engine, under 35 tons of thrust with a consumption of 300 kilograms per second of oxygen and hydrogen. So when the EPC is over, what happens is that, so at the beginning there is the EAP, as we will detail later, but basically at the takeoff you have the EPC, the central core, and the EAP switch on. Then after 2 minutes the EAP consume all the propellant, so they're going to be separated. And at the beginning, the central core, the EPC is going to give a thrust for roughly about 8 minutes. And when it consumes all the propellant inside, then it switch off. And the upper stage, the last one that you see here, take over until injection into final orbit. So why we do that? I mean, the basic of launcher optimization is that you don't want to bring to orbit any unuseful mass. So the idea is that you use the stage to thrust the launcher and to give thrust, but as soon as the stage is empty, it's basically a dead weight, and you want to get rid of it as soon as you can. This is why first you separate the booster and then you separate the EPC. And what arrives into orbit is literally the tiny last stage that you see here, and all the rest is following into the ocean, as we'll see later. So this is Ariane 5 ECA, which is the current version Ariane 5. I remember that the first version was Ariane 1, which was launched for the first time on December 24th, 1979. So 35 years ago. And from that moment to now, 5 versions Ariane 5 have been developed and been used. And now new Ariane 6 is going to be decided within the next few weeks. And it's going to be the continuation of this great family of launcher. Again, next slide, just few more details about the upper part of the launcher, in which, as I was mentioning before, 2 satellites are stuck at the same time. So you see on the lower part there is 1 satellite, on the upper part there is another satellite. And this is the very specificity of Ariane 5 to be able to launch 2 at a time. So that means reducing the cost. Also in this slide, some more specific about the different elements of the launcher. So on the upper side, you see what we call the VEB, which is the Vehicle Equipment Bay, which basically is the brain of the launcher. So it's a ring, okay, placed between the EPC and the SCA, and where all the electronic part of the launcher is installed. So the OBC, the inertial measurement unit, and all the electronic part that tell the launcher where to go and where it is, and the brain basically of the launcher. You have the battery, and you have all the electronic and smart stuff of the launcher is on this ring, okay? Which obviously is a carbon structures, and there are lots of studies about the different bending mode of this structure, because you have to be very attention when during the thrust phase with the thermal environment, that this structure doesn't bend so much. Otherwise, the inertial measurement unit, they are sensible to this change, so there should be an effect on the trajectory. So it's very complicated stuff, but we'll get through that a little bit later. The SCA, so that was the stage that I was mentioning before, and here we have a section in which we see that there is this central oxygen tank, which is the bulb in the very middle of the figure, and then you have a nice shape, which is the sort of half dome over the oxygen, which is the hydrogen tanks, and then obviously the red is the nozzle, and the chamber is just under the oxygen tank. It works for about 950 seconds, that added to the 8 minutes of the EPC basically allow you to get into GT orbit in 20-25 minutes. On the right side you see the fairing. So the fairing is these carbon structures that is protecting the satellite at launch. Because what happens, the satellites are inside this carbon structure, and during the atmospheric flight you have to be sure that there is a protection in terms of vibration, in terms of dynamic pressure, and in terms of thermal. So this fairing during final chronology, so after encapsulation, final chronology and launch, make sure that the satellite stayed within temperature, hygrometry, vibration threshold, because they need to be protected. A very, very fragile piece of hardware. So that's the purpose of the fairing. And obviously, like the stages, once you get out from the atmosphere and there is no more air, there is no more issue of heat, of vibration, it's separated and it's falling down on the ocean. So I was saying the fairing is protecting the satellite. Then you have the SILDA, which is the system that allows to have two satellites launch at the same time. So it's a big bell, it's a carbon structures, which is 6 meters high, so it's like 3 floors high, and it weighs just 500 kilograms. And so within there is one satellite, and over it there is another satellite. So this is the system that allows to bring two satellites at a time. And then you have the adapter, so this conical part that is very important because it's the actual interface between the launcher and the satellite. So the satellite is sitting on the adapter, which is this conical structure, and on the adapter there are the separation springs. So there is a clamp band, and when the satellite is in orbit, there is a launcher, there is an order sent from the launcher. The clamp band is open, and the spring can separate the satellite from the launcher. And that is, I would say, the end of the launcher mission and the beginning of the satellite mission. I'm going to spend a few words about Soyuz, which is the middle-class launcher of the European Space Agency. So the decision was taken on the beginning of the 2002, to bring the Soyuz, which was launched so far only from Russia, to Kourou, to this Guyana Space Center, and to launch it from there. So it was an agreement between the Russian government and the European and French government to be able to use the Soyuz from French Guyana. It was a big project. The launcher is exactly the same. Obviously, it has to be customized to the European safety rules, which are slightly different than the one applicable from the Baikonur launch site. But basically the launcher is exactly the same, and I would say I think is the most, without any doubts, is the most reliable launcher in the history, because the core is the same one that launched Yuri Gagarin back in 1961 as the first man in the space. Soyuz has been launched probably 1,850 times so far. For over 40 years, it was launched 10, 12 times per year. So in the 70s, in the 80s, very, very high rate of launches. It's a man-rated launcher because it's today Ariane 5 launch only satellite, but Soyuz has launched and is currently launching astronauts. So all the launcher is man-rated. So I would say that the standard of reliability and redundancy are triple and not double like on Ariane 5. Today the reliability is something about 98.2%. So if you apply it to 2000 launch, it means that very, very few launches failed. It's a very, very reliable launch, and this is why Europe has decided to put in place this agreement with Russia to be able to use it from French Guyana, and I will tell you why it's very interesting to be able to launch it from CSG rather than from Baikonur. In terms of elements, well, you see at the slide how it's done. So on the left side you have a section of the launcher, 4 solid strap-on boosters, which are separated like Ariane 5 as soon as they are empty. You have a fairing, which is the same principle of Ariane 5, and then you have the frigate upper stage, which is basically the 6 tanks stage that you see at the very top of the slide. It's an incredible simple stage. I mean, when you see like this, you know, you have 6 spheres. 4 of them contain propellant. So it's an hydrazine, it's a storable propellant upper stage, so it's not cryogenic like Ariane 5, but it's storable propellant. One spherical tanks contain all the electronic part, so the IMU, the onboard computer, and all of, I would say, the guidance, navigation, and controls unit. While the other one contains all the telemetry, antennas, and necessary to communicate with the heart and the ground station. So in the middle you have the engine. So this is basically how it works. You have something sticking out that you see. These are the hydrazine attitude control system thrusters that, as you see, they can do complete pitch, yaw, and roll control. So when you are into orbit, the stage can turn in all the sense using these 12 hydrazine thrusters. As I would say, there is triple redundancy, which means that which is needed for a man-rated mission. I'm not going to do the difference between hot redundancy and cold redundancy, but it basically means that you have 3 different ways of getting the information you need to have for accomplish the mission. In other words, you can tolerate 2 failure of 2 of the elements, and you still have the availability to achieve the mission. This is what we call triple redundancy. So you can allow 2 failure out of 3. That's the Soyuz. And then we go to the little Vega, which is the last to come in the Ariane launcher fleet. The maiden flight took place on February 2012. So only 2 years and a half ago. It's a 4-stage launcher, 3 stages of solid propellant, the P80, the Z23, and the Z9. All the 3 produced by Avio, which is an Italian company specialized in the space business. And then the upper part is the Avum, which is produced by Ukrainian Yasinoe. And then you have the fairing with the satellite up there. It's a very light launcher, and as we were saying before, it's for the low mass range of the satellite. And since it's very new, there is lots of technical innovation in this launcher, which I'm gonna tell you like before. One of the main things is that the thrust vector control, so the system that allows the thrust to be orientated, is not hydraulic like on Ariane 5, but it's electric. So basically an electric engine which allowed to steer this thing. So very reliable, low weight, no oil needed, so lots of advantages. You can see in the slide all the different producers from one another. You can see who does what on this launcher, but basically the section gives you an idea of how the stages are optimized between one another. So now we went through, I would say, the 3 launchers, okay, Ariane 5, Soyuz, Vega, how they are built, the main feature of one another, and as I was saying before, what all they have in common is the launch base. So they are all launched from the Guyana Space Center, which we call CSG, Centre Spatial Guyanais, from the French acronym. And this space center, which is called, I would like to call it European Spaceport, because all the European missions are launched from this site. And it's in South America, just above Brazil. There is French Guyana. And the city is Kourou, which is maybe 50 kilometers north of Guyana, the capital. And it's 5.3 degrees north latitude. So why this is so important? Well, first of all, if you look at the map and you see the location of this launch site, as you can see, is ideal because for 2 reasons. The first reason is that it's next to the sea, next to the ocean, and so it's perfect for any GTO launch, which are equatorial launch, because you take off and you go towards the east. So as soon as you take off and go toward the east, you are over the ocean. So you're not overpopulated area. So in terms of risk, it's much, much better. And also, if you have sun synchronous mission, so mission what we call SSO, sun synchronous orbit, in that case you have to go towards the north of the Earth, and also you have the sea, because you see the two yellow line show you exactly the trajectory when you go to GTO and SSO. And on top of that, it's very, very close to the equator, just 5 degrees latitude difference. And as you know, if you have done any class of launch vehicle performance, the performance of the launcher to GTO orbit is proportional to the cosinus of latitude of the launch pad. So it means that the closer to the equator you are, the more performance you get from the same launcher. So the more mass you can bring to GTO orbit. So today, if you compare, for example, to two very known launch sites, which is Cape Canaveral in Florida and Baikonur, you have 50% more with respect to the same launcher, but launched from Cape Canaveral, and 45% more compared to Baikonur. This is why it was very interesting to bring Soyuz, a well-designed, flight-proven, very reliable launcher, launched by Baikonur, to launch it from French Guyana, because you can get 45% performance more rather than launching from Baikonur. So this is basically the reason why today Kourou, well, not today, back in the 30 years ago, Kourou was chosen to be the European spaceport, because of the position and because of the performance of the launcher if they were launched from this place. Here is a zoom of the European spaceport. So, you know, if you ever go there, it's an amazing experience, because you can have guided tours. They bring you through all the different launch pads. They show you the launcher. It's a very, very nice area. So basically there is one road. What you have to understand is that you are in the middle of the jungle. So there is not a very, I would say, you know, it's not like being in a city in Europe. It's a South America. So the city are medium size. There are lots of people working, because the European spaceport is very, very active. ELA is basically the Ariane 5 launch pad. And then you have ELS, which is the Soyuz launch area. And then you have the Vega launch area. And they are very close one with the other. So this is just to give you a map of the two. And to finish a little bit this introductory part, and before starting with the next section, I would like to present to you, we're talking about the European launcher, we talk about the launch base, let's talk about what the others does in the world, how many launchers there are, from where they are launched. So this is a slide that in a very quick way present you the performance of all the other launchers and where they are launched. So to go very, very quickly, and starting from the east, where we have Tanegashima, which is the launch pad for the Japanese launcher, H2. We have the Long March, which is the Chinese launcher, which is launched from Xi'an. The Russian launcher, the Proton and Land Launch and Soyuz, they are launched from Baikonur or Plesensk for the SSO launch. Then you have Ariane and Soyuz, like I just said, from French Guyana, which is South America. Then all the American launchers are launched from Cape Canaveral in Miami, or Vandenberg, which is on the other side, on the Californian side. And then you have Sea Launch, which is quite an interesting concept, which pushed to the limit the idea of launching from the equator, because, as I say, the performance of the launcher is proportional to the vicinity of the equator. So the closer you are, the more performance you have. And so sea launch concept is that you basically go to the equator. So you take the launcher from the Californian coast, you bring it to a launch pad, which is a refurbished oil platform in the middle of the Pacific Ocean, and you launch basically from 0 degree latitude, which give you the most performance you can get from that launcher. So again, you can get through the numbers. There is the Atlas launcher, the Proton, land launch, sea launch, Delta, GSLV. They are launched from India. So the GSLV is the geostationary launch vehicle, and the PSLV, the polar launch vehicle. And you can see the performance of the two of them. So this is basically very, very high level European launcher, the competitors' launcher, from where they are launched, and the importance of the launch site, the launch pad.